Welcome to the video corresponding to deliverable 7.6, design of the benchmark tested for robotized ironing and garment folding final of work package number 7, use cases of the project ALMA, human-centric algebraic machine learning. This work package consists in combining the potential of algebraic machine learning with our own efforts at Universitat Madrid in humanoid robotics, specifically in the domain of domestic tasks, focusing on the laundry pipeline, specifically on the tasks of ironing and folding/unfolding garments. Let me introduce you to the humanoid robots To, developed at our own university, and Tiago, which is a commercial platform by PAL Robotics, which are both further described in the deliverable document. What we are seeing here is a visualization of the 3D colored registered point cloud, which is obtained by a single view of either of the two platforms, which is applicable to both of the tasks, therefore is presented jointly. Before we delve into the robotic demonstrations, we can see the robotics lab of Universitat Madrid open source repositories, which if we filter by ALMA, we can find 4. We can first see the gymnasium environments, which are separated into the two tasks, which give us a notion of the kind of tasks that we will be performing in their mathematical formulation. The ironing tasks is formulated as an MDP, that's why we are using a gymnasium to represent Markov decision process. And for that we developed a small bandit, which is a stateless MDP, then a grid roll, which actually has states, but the objective would be only one, and finally, much closer to the ironing task would be that of the two-dimensional with many objectives. And it turns out that this scales up to the 2.5 or 3-dimensional task, because the commands that we are sending are equivalent in the 2D case of the fake ironing, up, down, left, right, versus up, down, left, right. It's all equivalent, and this tail ironing can actually also connect to the real robot. The ports here are of type JARP. In the case of tail ironing, can also connect to the real robot, and the ports here are of type ROS. And regarding the folding task, here in fact we're reusing the gymnasium structure, but we're not using the same type of reward. Instead, we have specific rewards. In the fake folding environment, it loads the data from the dataset, which we will see, where you can actually download the dataset generated with the dataset generator, and the task is you obtain the image and you have to guess the pick and place points. So it's modeled in fact as a supervised learning problem, and specifically a problem of regression, where you have to predict the pick coordinates, which are 2, and the place points, which are another 2. So 4 output values of the regression. And again, everything is mapped out to be transported from the image space to the camera space to the robot space to the robot frame. So everything is kind of simplified. All the logic is input at one part through here, and on other parts of the actual environments we'll go through. All of the transformations are in fact part of the environments. That's why we're going through them slightly slowly. In ironing, tail ironing, you can see how the application for simulation, for example, loads the simulator, and also, for example, this, which is the kinematics. Okay, these are the environments which encapsulate quite a bit of logic. Then we have the actual solvers. So the main target of this project is algebraic machine learning. Therefore, the focus will obviously be on this repository. It's the one that has possibly most commits if we go through that, okay, throughout the years. And here we again have it separated in folding and ironing. Start with ironing, which is modeled as a reinforcement problem. In fact, we had two approaches as explained in the deliverable. On one side, it's more in the domain of reinforcement learning. So we're using the cross entropy method. And then we also have the more path planning like method. And then for folding, it's more supervised learning. So these are all scripts until we get to something functional that works like supervised learning. For the regression problem, to train the supervised learning is precisely where the data set comes in place. Okay, so here we have this data set generated. It generates samples like this, and we also have a visualizer. And since we actually have a data set for that case of folding to establish a baseline, we also developed a small neural network just to compare results. We can now move on to the demonstrations of these environments controlled by the AML controllers. We can skip the bandit and move on directly to the grid world, where we can see that we're training at 4x velocity, and that would be the testing pretty slowed down. The jump to fake ironing, which is in fact ironing in 2D, is very direct because it's just changing to have more objectives. And in fact, the way that everything is structured from the perspective of the AML agent, be it in the CEM, cross entropy method iteration, or the path planning iteration, it's in fact all the same. We have the up, down, left, right, and diagonals commands, which were commanded to the 2D version, to the simulated 2, and now on screen what we have is the Tiago humanoid robot, which in the observation space is perceiving the wrinkles as the same squares that it was seeing in simulation. This was a frontal view of Tiago and the zoomed in vision of the wrinkle. Once it's done, it retrieves the iron. That's automatic. And this is a perspective which is closer to the RGBD sensor that you saw at the beginning. Many roboticists accelerate the velocity of their videos. Here, unless indicated otherwise, everything is at 1x. And with this, we can move on to the robotic folding task, specifically unfolding. Here we have a visualization of the folding dataset, which is public, has these images and their ground truth. The fake folding environment loads these generated images. The actions are setting pick and place operations, and in return you get the error with respect to the ground truth. In the case of fake, in the case of the robots, there are no ground truth in simulation or with a real robot. Therefore, the score that the agent is provided with is the rectangularity, under the assumption that the pieces of cloth are either square or rectangular. This assumption is a simplification with respect to other methods that we have published in the past, but it is due to those methods being ad hoc and instead this being a learned procedure. In fact, since it's formulated as a supervised learning problem of regression, we could actually compare it for the first time to a neural network. The voiceover of this video finishes here, and the rest of the video that remains is at velocity 1x of many executions of the Tiago folding environment connected to the real robot. Thank you very much. We hope you enjoyed. Thank you for watching until here.